For countless generations, humanity has gazed upward into the infinite ocean of stars, driven by a deep and almost instinctive curiosity about the cosmos. That curiosity has followed us from the earliest civilizations, when ancient observers traced patterns in the night sky, to the present day, where advanced observatories capture light that has traveled billions of years to reach us. Across time, the questions have remained remarkably consistent. How did the universe begin? What forces shaped it? And how much of this story can we truly understand? During the 20th century, scientists developed a powerful framework known as the Big Bang Theory, offering a coherent explanation for the origin and evolution of the universe. According to this model, the cosmos began approximately 13.8 billion years ago in an unimaginably hot and dense state, where space, time, matter, and energy were all compressed into a single evolving origin. In the first fraction of a second, space itself began expanding, not into emptiness, but as the expansion of space itself. Time, matter, and energy emerged together, forming the foundation of everything that exists today. Over billions of years, this expansion led to the formation of galaxies, stars, planets, and eventually, on at least one world, the emergence of life capable of asking questions about its own origin. The evidence supporting this framework is extensive and deeply interconnected. The cosmic microwave background, a faint afterglow of the early universe, fills all of space and acts as a fossil imprint of the earliest moments after the Big Bang. Distant galaxies are moving away from us, their light stretched into longer wavelengths in a phenomenon known as redshift, revealing an expanding universe. On the largest scales, matter is arranged in a vast cosmic web, filaments of galaxies separated by enormous voids, matching theoretical predictions with remarkable precision. And yet, even with this strong foundation, the Big Bang Theory leaves some of the most fundamental questions unanswered. What triggered the expansion? Why did it begin at all? And perhaps most intriguingly, was there anything before it, or does time itself begin there? In recent years, these questions have taken on new urgency due to observations that challenge our understanding of cosmic time and structure. One of the most fascinating examples involves ancient stars whose ages push the limits of current cosmological models. Some of these stars appear nearly as old as the universe itself, forcing scientists to re-examine how stellar evolution is calculated and how cosmic timelines are constructed. Determining the age of a star is an extraordinarily complex process. Unlike objects on Earth, stars do not carry obvious timestamps. Instead, astronomers rely on indirect measurements such as brightness, temperature, chemical composition, and motion through space. These observations are compared against detailed computational models of stellar evolution that simulate how stars change over billions of years. Even small uncertainties in these measurements can lead to differences of hundreds of millions of years in estimated age. Another method involves stellar rotation. Over time, stars gradually lose angular momentum through magnetic braking and spin more slowly. By measuring this slowdown, scientists can estimate how long a star has been evolving. However, this method becomes less precise for extremely old stars, where accumulated uncertainties begin to overlap with the age of the universe itself. This leads to a deeper and more uncomfortable question. How certain are we about the age of the universe? To better grasp cosmic time, imagine compressing the entire 13.8 billion-year history of the universe into a single calendar year. In this cosmic calendar, the Big Bang occurs at midnight on January 1st. Galaxies begin forming only after the first few months of this compressed timeline. Our solar system does not appear until late December. And all of recorded human history occupies only the final seconds before midnight on December 31st. This perspective reveals just how vast and almost incomprehensible cosmic time truly is, and how recently humanity arrived in the cosmic story. Astronomers estimate the age of the universe primarily by studying its expansion. As light from distant galaxies travels toward us, it is stretched into longer wavelengths, appearing redshifted. By measuring this redshift and combining it with observations of the cosmic microwave background, scientists arrive at the widely accepted age of approximately 13.8 billion years. However, this framework is not entirely settled. Small tensions continue to appear between different measurement methods, particularly in the rate of expansion known as the Hubble constant. These discrepancies do not overturn the model, but they suggest that something subtle may still be missing from our understanding. Within our own galaxy, new data continues to reveal unexpected patterns. The Gaia Space Observatory has mapped the positions and motions of nearly 2 billion stars, producing one of the most detailed three-dimensional maps of the Milky Way ever created. This data has uncovered subtle irregularities, particularly in the outer regions of the galaxy, where stellar motion does not always match predictions from existing models. Some stars appear to move in unexpected ways, hinting that the distribution of invisible mass may be more complex than previously thought. This brings us to dark matter, the unseen substance that exerts gravitational influence across galaxies. Although it does not emit or absorb light, its presence is inferred through gravitational effects on visible matter. And beyond that lies dark energy, the mysterious force driving the accelerated expansion of the universe. Together, these two components dominate the cosmos, yet remain largely invisible and poorly understood. Modern observatories are now pushing deeper into these mysteries than ever before. Advanced instruments can detect faint infrared signals from the earliest galaxies, analyze the atmospheres of distant worlds, and peer through cosmic dust that once blocked our view of the early universe. Each new observation adds another layer to the puzzle, and with every layer, the picture becomes more complex rather than simpler. Some early galaxies appear to have formed faster than expected. Structures emerge earlier than theoretical models predict. Ancient stars continue to challenge established timelines. And distant signals hint at environments far more active than previously assumed. These findings do not necessarily overturn existing theories, but they push them toward their limits, exposing where our understanding is incomplete. Science, however, is not weakened by such tension, it is strengthened by it. Each anomaly becomes an opportunity to refine models, improve instruments, and rethink assumptions that once seemed unquestionable. The history of science is filled with moments where established ideas were reshaped by new evidence. We may be witnessing one of those moments now, where refinement leads not to collapse, but to deeper understanding. The universe is not a simple system governed by perfectly predictable rules that are already fully known. It is dynamic, evolving, and operating across scales of time and space far beyond human intuition. Somewhere within faint starlight, ancient radiation, and subtle gravitational effects, answers are still waiting to be uncovered. And as exploration continues, we move closer not only to understanding the universe's origins, but also to recognizing the limits of our current knowledge. Perhaps the most profound realization is not a final answer, but something deeper. That the universe is far more intricate, far more dynamic, and far more mysterious than previously imagined. An ever-evolving reality that continues to challenge human understanding, constantly expanding the boundaries of what we think is possible. And in that sense, every new observation is not an ending, but the beginning of a deeper question, one that leads further into the unknown.